Hey, what's up, SolidWorks fans slash football fans? I almost said the other word. The big tournament. We got to be careful around saying that word, but I'm happy you guys are joining. We're in the final stretch here. We've got the big game, the final match coming up this weekend. So I hope you guys have been watching along with all the excitement. It's been a really fascinating tournament. I know, Ron, you've been in it, right? You've been watching.
Quite with quite some passion, Mike. It's been a crazy month and a week or something like that, month and a half.
Yeah.
But really, lots of ups and downs. A lot of emotions. Very invested. As much as I mean, I should not be that invested in a sport, but it's been like when the team wins, it's a good week and a good day, and then when the team is not winning, it's just like, oh man, I'm sad.
It ruins the day. It
Yeah.
really does. Well, unfortunately, we're probably going to upset the audience today. We're talking three insane hot takes about football that sound completely ridiculous, and I hope you enjoy our hot takes. And we're going to try
Yeah.
to prove every one of them using engineering and using SolidWorks, right? So this live design, we'll do a little design, get in the CAD. I want to show just kind of some geometry stuff, but then we're also going to break away from design and get into simulation.
Yeah, yeah, Sean. Sorry, Mike. We're gonna talk about some physics. We're gonna talk about how we've used our simulation suites to analyze the football and how smart things have gotten. So there's a few different good takes that we're gonna be running through, the spherical balls and is technology ruining football. So we'll upset some people, but we're not sorry about it because it's football and it's passion, and let's have a good time. And out of these topics, Mike, which one do you think which resonates most to you?
Oh man, that's a good question. I think our second topic is really big. The first topic on geometry is really interesting, and just the ball design. And yeah, all of them. we'll, have
All
to,
of them,
we'll have
yeah.
to
I
dive
can't wait
into
to
the
deep dive
audience.
into all of them.
Yeah. Well, let's get started, man. I think our first hot take that we're going to dive into is spherical balls are the worst kind of balls, which is an interesting topic, right? You and I, Ron, we dove really into the evolution of the soccer ball, going back to the days of like the leather team model in the early 1900s. Before then, balls were used all over for, the Hang Dynasty used them in China for Sun Tzu or something like that. The game they played with their foot. But generally we think of a ball, we think of a sphere. I always think of just like the classic dodgeball, which obviously isn't used in soccer, historically has not been, but an element of this is used in modern day, the bladder itself. And we'll talk more about the construction of a football as we get into some of the materials. But something like this wouldn't necessarily work because of multiple factors, right? There's a lack of control, but more so like the manufacturing of this. Historically, back in the 1900s, they used to use it was later than that, 1970s, they started using a rubberized bladder. Before
Mm.
then, it was actually a pig's bladder. That was what's inside of the ball. But these things get a ton of heavy usage. Obviously, they're kicked, they're scuffed, and so on. So something like this wouldn't hold up. So if you look back at the history of the ball, we get into that classic T model leather ball, and this was like 1900 style
Mhm,
ball
mhm.
to it. It's paneled. It does wrap around a pig bladder itself. But the problem with this ball, and we'll get more into this later, is like it absorbed a lot of water. What we do see though, it is paneled, and that's something that hasn't changed since like the early footballs. Is they've had some sort of panel to design. Now, this isn't the current day Trienda World Cup ball. The Trienda World Cup ball has four panels, and we'll talk more
Mhm.
about this. This ball here is more of like the standardized what we think of when we think of a World Cup or of a soccer ball. This is the 32 panel. It's known as the Buckminster ball. And more commonly, you see it as like black and white. And Ronit, do you know why it was black and white?
I actually don't, man. Why was it black and white?
Chat, I wonder if you guys know why was the original soccer ball, football, when they did this Buckminster ball, if you guys know, put it in the chat. If you don't respond, I'll tell you the answer here in a little bit. But this is the one that I was most intrigued to learn more about the geometry. So I cracked open SolidWorks and I went into an exercise of like, hey, how do I figure out the panel structure of this ball? Because it's a lot more complex than you look at it. So started to do some research, and I learned that this is based on a shape called a pentagonal antiprismatic pyramid that's mirrored and has triangulation inside of it, and this makes an icosahedron. So this shape you're looking at now is an icosahedron, and that shape is what actually derives the location of each of those panels. So let's jump over to SolidWorks, and I want to show you the thought process I went through to figure this out. There are a lot of tutorials online on how to model a soccer ball, and they're all relevant. If you want to model a paneled soccer ball, this is more about that core base geometry of how you find the locations of each of these. All right, so Ron, geometry. I'm going to quiz you on a couple of these things, and same with the audience, and see what you guys can answer here. We have here, this is looks like a pyramid. We've got 5 sides. So 5-sided hexagon or 5-sided shape is what?
A
Pentagon, correct. A 5-sided pyramid, this is called a antiprismatic pyramid. So when you create a 5-sided, antiprismatic pyramid. So it's not a prismatic shape, that's the antiprismatic, but it is a pyramid. So anytime you have 5, 6, 7, so on pyramid shape, it's an antiprismatic pentagonal pyramid. The pentagon is key here. The short name that you'll learn about this is called a pappy. So if you ever heard of the word pappy or you want to throw that around, that's what this is. So I started off with a pappy shape, and then I wanted to go through and start to what they do is called a truncation. And that's literally this little top here. I just cut this off. I just use a 2D sketch and slice through the top of this. And what that gives me is a representation of a smaller pentagon, right? What you'd expect. So I've got the top of the ball kind of figured out here. And of course, we're just going to mirror that down to get the bottom of the ball. This part was like pretty easy to figure out. We got 2 truncations on that pentagonal antiprismatic pyramid, or a poppy. So I did that. But then what we do is we need to rotate this bottom one. So I just used a move copy body in the tree here. I'm just going to fire that in. And that was at a distance, was pretty easy. I think I got it on my first guess, was just 180 degrees divided by 5. And that gives you the right offset. And what we're doing is we want to line up this vertice. So it's set up to the midpoint of this line here.
Got it.
And that's really the base structure of where that icosahedron comes into play.
So one more time, Mike, what's that word again? Icosahedron.
Icosahedron. That's the core shape. Yep.
We had Jesse ask that name again because it's kind of it's a tongue twister for sure.
I know. This,
all right. Crazy.
Man, I thought this was going to be an easy exercise, and I challenge any basic user to advanced SolidWorks user to go through creating complex spherical shapes that are based off of these icosahedrons or tetrahedron types triangles, because it brings up a lot of like trigonometry that you haven't used in some time. I will admit I used Claude for one thing. I just had to look at an angle, and that was the face angles between these panels. But the rest of it was trial and error, and I'll finally show you how I got to the final shape too, which was really fun. So icosahedron is what we are building, right? The core shape is going to be an icosahedron. We're starting off with 2 pentagonal antiprismatic pyramids, or poppies, that are truncated.
Okay, yeah.
I know,
truncated pappies. I can say that. That's easier.
Truncated pappy. There you go. So then from there, I went through and I just started using a 3D sketch, and I connected these dots. This was just referencing a picture of an icosahedron. That made sense. I created the first set, did a surface fill. I love using surfacing tools. They're kind of the core and foundational parts of what solids are in SolidWorks as well. If you're not familiar with surfacing, I recommend don't be afraid of it. Dive in, learn it, do some tutorials, play around with it. It's a great tool to learn to start to be able to create a little bit more complex. You could do this with solids, but I thought this was a better representation to kind of illustrate how this is built.
Right.
All right. So 2 surface fills that are just going to be the corresponding, and these are almost a tetrahedral, but they're not. I was diving into that wormhole, and I found out that you can't use a tetrahedral to fill it. So I just did an outer shape, and this is just a mirror, right? Or sorry, a circular pattern around that center, the center axes. So we got those. Let me go and I'm just going to tab hide. If you're not familiar with this awesome, oh, my keyboard's not wanting to work. 1 second, guys.
By the
There
way,
we
like
go.
Mike, this looks like, when I was a kid and we didn't have a football, we would just stuff things in a sock, and it would have this shape. So it looks like the football I used to play with when I was a kid.
Lumpy.
Yeah,
That's awesome. So yeah, I just did, I just hid the top and bottom solid bodies using a tab, just to show you that I then just copied the surface of the
got
pappy,
it.
sorry, to create that top and bottom face to it. And this is going to get me the center object. And I wanted to look this up. There is a name for it. I think it's pretty generic to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, to a 12-sided,
Mhm.
13, 14-sided object. I think there's a more core name to it, but I didn't get that far. All right, so 2 surface offsets, just knit this up. Now it's a solid.
Yeah,
So we got 3 solids, and then we have our truncated pappies on top. Now, this is where I wanted to get to the core of the ball, but from here we needed to start to truncate the rest of the pyramids. And I couldn't think of a really great way to do it. This sketch here is just driving the center point. So I
got
needed to
it.
reference that if you can see it.
Yep.
And then I just used 3D sketches.
Okay.
And for some reason, I think all the graphical information I have is slowing my session down. So let me show you this. This is pretty cool. All right, here's our shape. We're going to start looking inside of it. And what I did is I created a 3D sketch, and in that blue line, hopefully you can see that. And if you didn't know, you can change colors of sketches.
Yep.
Maybe we'll do this to something a little brighter. I like that red. You can right click on a sketch and create the sketch color. This is a nice way to be able to show exactly kind of processes that you're going, like I'm doing here. And you get this really cool internal design. And this is basically construction lines from the center point that move out to each of these vertices.
Got it. Yeah.
Now I wanted to do one more, and I just basically created a standard sketch, 3D sketch again. And these are all equal length, but you'll notice up here, there's a little gap.
Right.
This dimension is driven by that truncation dimension.
Got it.
All right.
Okay.
The truncation was done on the cut extrude.
Mm-hmm.
And this sketch 6, that's all that is driven off of a global dimension of, right now it's set at 2. We did a discussion of global dimensions and equations a while back on Live Design. I'm a big fan of using them, but this lets me just reference this one dimension, and I'm going to use that to drive it later on. Okay, so I got all that laid out. Then I went through and I just created some reference geometry using planes. And here's a really good tip for the SOLIDWORKS users. If you need to create a plane that's going to be normal to an endpoint, you can use the reference plane geometry, click on the line, and then you can click right on the end of the line, and it fully defines that right there, which is a pretty slick
That's a
way
great tip, Mike. I use that one quite a bit.
all the time. Yeah. So I just went through and did that for each one. That took, like a minute. It really super process or easy process to go through. And now this is getting pretty crazy. Let me turn off these internal sketches. We don't need to see those. I want to show you we have all these planes, and these planes are now going to truncate my solid shape.
Got it.
So let's go through. I just use a surface cut. So if you didn't know, again, surfacing tools, super powerful. The surface cut allowed me to truncate each edge. Now let me hide this. We can take a look at where we're at.
Wow, look
All
at
right. That there is the core shape of a soccer ball.
Look at that. Oh, I can
Let's
see
go
those
over.
pentagram shapes as well that you see on one of those old footballs. By the way, the question that you asked, Mike, regarding the white and the black, why there was different. We had Gurpreet answer that pretty nicely, and I think it works. So he said, like, they were black and white because they should be visible on a black and white TV. The ball should be visible. So
Yeah.
is that the right answer?
Yeah, that is correct. It's twofold. It was the core of that was when the World Cups, the soccer game, started to, the big tournament started to televise. Back then was the original part. They wanted to get viewership. They saw it was very difficult to watch the ball in that leather shape. So they started to do it black and white panels to make it visible on TV. The players then came back and said, oh, it's also easier for us to see the ball. So
Yeah.
that's why they stuck with it for so long, was based on viewership for both the audience. The TV audience was the core reason, and then the third was the players also liked it.
Yeah, I've played with that black and white ball, Mike, and what I enjoyed about that was like when you put like a spin on it, when you kick it, and you see that spin, that black and white, going. It looked very cool when it's spinning like that.
Oh, for sure, I bet. For those in the audience that don't know, Ronit played at a uni level football, so he's very involved in the sport. Has been his whole life. He's a good soccer player, even to this day. He's still has got some good moves.
Little bit. Thanks, man.
All right, so Ronit, I'm almost done with this, but this is where I ran into the biggest, like, I had a scratcher. I was grabbing scratch paper and drawing out triangles and doing trigonometry, and what I couldn't figure out is how to create equal sides for every one of these shapes. And we have essentially a pentagon here all across the ball, and each
Yeah,
pentagon is surrounded by hexagons.
correct.
And that's something I didn't really realize. I think was I always thought that a standard soccer ball was all just paneled by hexagons, but no, it's pentagons and hexagons that build up this overall shape, that build up the icosahedron, truncated icosahedron.
Hmm.
So what I did is I combined everything. We got one solid body now, and then I gave up and I did a design study. And I think design studies are probably one of the most underlooked things inside of SolidWorks. They're
Oh yeah.
phenomenal. And I set this up to use that global variable, so that truncated depth, that was that 2 millimeter cut down on the top and bottom.
Okay.
That also drives the location of that 3D sketch inside. That's where all those planes are created. And I said, hey, run this from 3 to 15 millimeters in 1 millimeter increments.
Okay.
And then what I wanted to do was monitor, and I just created a sensor. And the sensor is based on just the measuring tool. If you didn't know, in Evaluate, under Measure, you can select an edge, and you can actually create a sensor right here. This is the little graph, and that will report back anything that you're measuring and track that for you. Those sensors become a folder, which are over here. So I have the pentagon length at 3.81 millimeters, hexagon at 65, not even close to the same length.
Sure.
All right, so that's the setup, right? So what am I varying? The truncated depth global variable. And all I'm doing is just watching this. I just want the data. All right. So I'm going to run this. And what SolidWorks will now do, if I can zoom out, yeah, because this is the fun part, is SolidWorks will take and start to modify that truncation variable and then iterate through all of these and then kick out each iteration. It's changing. So 9.52, 11. And I'm not going to get an exact value here. There are ways to do optimizations inside of here. There's no equals, and I just want to find out where they're equal. So I'm just looking to the convergence of the pentagon length and the hexagon length.
Mm-hmm.
We started off, one was super big, one was super small. Where do they converge? Where do they cross over? And then I can repeat this design study and do it at a finer incremental rate, right? I can say, like right now we're seeing scenario 11's at 20.95, 22, 27. It's solving these through, and then I can use the scenario to figure out where are they close, right there. So 22 to 24, 27 to 23.
Yep.
Between 12 and 13, they crossed over.
Yep.
I can come back and start at 22 at scenario 11, and then right here we're at that truncated depth of 12 millimeters. That's looking pretty good. That's almost a soccer ball.
This is cool, man. This is so cool.
And it's simply enough. Just come back to this variable view and just say, hey, you know what? Let's start at 12 and let's go to 13.
Okay.
And let's do this at a 0.05. Yeah. Okay. And run this. And then it's going to do the same process to come through and give me the exact value. Now, that shape is a truncated icosahedron. It's based on everything we walk through. And this is how a soccer ball up to 2010-ish, I think, was pretty much, maybe it was before they started to play around with the geometry in the big match where they broke away. But that's when they moved in 2010. They moved away to what was it? The Jabulani You remember that
Jabulani
ball?
ball, yeah.
The 2010 ball?
That was a fun
So
ball.
let's go back to the hot take. Spherical
Yeah.
balls are the worst kind of balls. They are, because no soccer ball is perfectly spherical. They have grooves, they have ridges, they're comprised of panels. The paneling process is there to have a stronger outer. They used to be leather, right? Then it went to a polyurethane. Right now, modern day footballs are built out of polyurethane panels that are heat bonded. They're no longer sewn. It always was sewn, but there's strategy behind these panelings. And now the modern day ball, which we're looking at the Triunda, that ball is based on a tetrahedral. So it's not as complex, but it's four panels, less material, has a
Hmm.
lot of symmetry. I wanted to go through that process. I just didn't have time to start it with a tetrahedral and go through it.
Hmm.
But I do want to urge the audience to do an exercise like this because it's really fun and leveraging design scenarios to figure it out. We got our convergence right around, it's in here somewhere, 23 point, yeah, 12.6 ish is where we're converging or so. 12.8 right there.
Yeah,
Yeah. So right in here is our
yeah, very
convergence.
close. Yep, yep.
So
That's
yeah,
that's
spherical balls are the worst kind of balls because they don't hold up and you need some sort of texture to the ball to make it playable. So,
right.
on it, tell me about 2010. What happened then?
Yeah, man, that was a fun global tournament. So what happened in 2010? The company that is bringing all this tech in sports. They wanted to make the perfect ball, and in some sense, they achieved that perfection, Mike. And they achieved that perfection by, it went from like a 32 panel, ball to like you mentioned, there was an 8 panel thermally bonded ball without your seams and all that stuff, or minimum seams. So when this ball was used in the tournament, and by the way, just to kind of point out, this was a case study that was done by NASA as well, because it was a great case study. Proves like why we need to test and simulate our products before we ship it out for the consumers. So going from a lot of different panels to a 8 panel thermally bonded ball, of course you reduce the number of seams as well. Not just that, the grooves and the seam, everything got reduced. So when this ball was being used in the tournament, it was just like ultra smooth on the outside. So at very high speeds, I think about like 40, 50 miles an hour, when, is this ball could not predict if the boundary layer, or if the flow, or, airflow around it needed to be laminar or turbulent, it would just switch. And so
Oh, really?
imagine, yeah, imagine as a keeper, like you've got a striker who's hitting the ball really hard, and you have been practiced and trained to, like, figure out the motion of the ball and which way it's going to go, and your body's going all in that way to stop this goal, and all of a sudden at 50 miles an hour the ball changes the direction and goes in a completely opposite way, just doing something what we call a knuckleball effect. So it became very unpredictable. So
Like pure
a lot of
chaos introduced into a controlled sport.
big chaos. I was enjoying the chaos from the sidelines and from the TV, because I'm just like, what is happening with this ball? And having played the sport, I was thinking that all the players are just so good now that they can all knuckleball, very easily, which was not the case. It was actually the ball doing a lot of that physics. Now, of course, that was a problem, and the way to overcome this issue in the next, big tournament that happened in 2014, I think the ball was called Bazooka or
Oh,
something
right.
like
Yeah.
that. Yeah, yeah. What they did, that they introduced a little bit more of the surface blemishes, and the groove. They actually made the grooves a little bit more deeper, so it created that non-uniform sort of a boundary layer. So not that non-uniform boundary layer made the football, the path prediction a little bit easier to be done.
Oh,
So
that's cool.
yeah,
So yeah,
so
the technology of the football has been basically going from pig bladder to leather ball to a rubber bladder with a
yeah,
cotton liner on the outside to help
yeah,
with wear and tear,
yeah.
and also with the friction coefficient that happens between the outer and the inner bladder. They want that
Mhm.
to kind of be not get caught up. And then they went in 2010. They went into a. We said, was that the Jabulani was a 4 or 6 panel?
I think it was a 4 or 8 panel, one of those, like
Eight
with just
panel
less panel with with thermal bonds, so there's no
thermal
seams.
bonded polyurethane outer. And we learned the big thing was water was the reason they had to move away from leather, was because of
Mhm.
the water absorption during wet games or when high saturation on the field. To today's ball, which is a 4 panel based on the tetrahedron shape, right? Um, which is all like really interesting technology. That if you think of the history of soccer, the biggest technology change we've seen, is it the football? Because I mean, I feel like technology almost ruined soccer with the Jabalani ball when we pulled
Yeah,
back.
not
I
just
don't
the
know. I think this is
football.
our second hot take: was technology is ruining football.
There's a big debate we can do, and would love to hear from the chat as well, like what they think about, like, technology in football. I mean, of course, there's going to be pros and cons and stuff, but there's that emotional human aspect as well that's missing. But yeah, Mike, you're right. Like the football has just not stopped at like in improving its, what do you call the materials, and like going from pig bladder to rubber bladders and all that stuff. It's a whole system in there, and now it has all these wireless and electronics and antennas and all that stuff. That make it a
Antenna?
very smart tech modern football. Before we jump into that, Mike, there was a question that popped up. That was regarding, like, what other footballs. I think it was like something regarding what else we can do with the design studies in the football. I saw that pop up somewhere. Let's see.
Oh, a question came in.
Yeah, question came in, right. But I think so. When it comes to design studies, and Mike, you can kind of talk a little bit more about it. I also use design studies to use the engine that has been given to me to take away all the hard work, where I don't need to tell what dimensions to change to give me an optimized product. And this optimization can be based on many different things. So, for example, let's just take this football example. Let's say, if I was designing this football and producing it, and like I'm running these simulations on it, and I'm not liking how you know what type of deformation is happening on that, or the stress levels on that, so I can actually use those values as well, and bring it into an optimization study, which combines with the design study, and kind of give it, hey, keep the stress value or the displacement value or the deformation value in a certain range, and give me all the correct scenarios, and it will spit out a nice design for me that also takes in considerations the mass and the stress values, the deformation values, so you can actually tie all of it in together into the design study, which we will also call it as an optimization study. This is just to answer that question that
Oh,
popped up.
sure.
Don't see it anymore, but yeah, so going, go ahead.
I've got my audio coming through from a narration on this. So if you hear that, I apologize. So yeah, I guess the biggest technology change, minus the ball, and I'll play this video so you can kind of talk a little bit more about this around it. But what's
Mhm.
going on inside?
All right. So if you get a chance, if you have extra $80 to spend, just get the new try on that ball, or just get the new football and chop it into half, and you'll see the inside. We've got all sorts of wireless tech in there. We've got an antenna, we've got sensors in there, and this is where, like, the crossroads of engineering, simulation, sports, electromagnetics, everything is getting all combined together, Mike. This is not just a ball anymore that you kick. This is literally a walk, like moving data gathering, a device basically. So, in the past, and this is the hot take: is technology ruining football or not? So, I'll talk a little bit about, like, what it was without it, and then what it was with it, and we'll have the chat decide, if they think it's ruining football or not. But man, a few World Cups ago, I of course I supported England a lot, and then I remember Frank Lampard had a goal, they hit the post, goes inside, comes right out, but the refs didn't give it as a goal,
Yeah,
and the team was eliminated. Same thing. Let's go even further back, and where there's a team playing against another team, and there's a very famous scene in the history of football. It's called hand of God, and where this player literally used his hand to score a goal, and it was given. It was given. So, so that used to be the old case scenario where you all these errors that have been made by, the refs, because again, like, sometimes they don't see it because there's so much going on, Mike. You've got so many different angles. You've got the ref running around after the ball. So of course they are going to make mistakes, right?
Sure.
Now, the modern systems developed to make this a lot easier. So, you know, it's one of those. Now we've got all this tech inside the football, then we've got goal line high speed optical trackers and cameras, and to decide where the ball actually is. But what we can do is, like, for calls like offside, and we've seen those in this tournament as well. Seen some, like, not fun calls by the officials, but the sensors and the electronics that are embedded in it, what they do actually, Mike, they take something called an inertial measurement unit. We call it IMUs. And what these IMUs does, like, anytime there's a touch happens, anytime a spin happens, acceleration happens, contact happens, it registers that data. Not just register that data, you also have to be able to relay this data back to the refs in real time. So the modern inertial measurement units, Mike, they can operate, I think, around like 500 hertz, which is, I think, like 500 times a second of data is captured, right? So quite a lot of frequent data capturing over there. So the reason behind that is, you've got higher frequency means the more sample data, the more resolution, more accurate reading, right? Not just that data, like I mentioned, this has to be transmitted back to the from the ball to the receiver, from the receiver to to the refs, right? So we need some really low latency communication as well to make sure everything is going well. It's chaotic. And now think about this, Mike, where this football is actually in a stadium, where you've got all sorts of, electronic devices. You've got phones, you've got, like, broadcasting stuff, you've got a lot of chaos that's happening inside a stadium over here. So what can we do to, to make a ball that's going to behave properly with all these chaos that's going on? Mike, antennas are very tricky. So you could have the best design in an antenna, works amazingly well, does all sorts of beautiful signals and stuff. And as soon as you bring that antenna into around a certain material, so for example, in a football or in a stadium where you've got all these, like I mentioned, the broadcasting devices and the phones and this and that. So there's a lot of chaos going on, and the signal, what it does, it's not as smooth. Like, it gets bounced off, it gets like, and you would not know this until and unless you have your ball, you've got the sensor, and you've actually used it in a stadium. Or you can use the our EMAC capabilities, and you can use, first analyze the antenna itself, then you analyze the antenna, inside the football, and you will see how, like, the signal integrity has changed, has dropped. But it allows you to optimize that signal integrity based on, like, based on those materials that you've been working with.
Sure. And that was the last, we had the two little graphs coming up, right? It was they're
Yes,
shifting that signal to be exactly where it needs to be because of all of the other noise that occurs in here.
correct.
And Rana, this is CST Studio Suite. This is doesn't look like SolidWorks, but it is a SolidWorks product. Do you want to talk a little bit about what we're analyzing here, or what we're seeing?
Absolutely, man. So what the awesome colors that you see over there. So that's actually where the ball positioning is. The ball has an antenna, and it's transmitting all these signals, right? And where you see where all those blues are, and you got the circles and all that stuff. That's where things are reflecting back. So you want to be able to make sure when you've got when you've got a design, you've got all these electromagnetics, antennas, GPS trackers, and all that stuff that's happening within a football. You want to make sure the signal integrity is strong. So you want to
No,
be able
no
to
dead
transmit
spots,
the
right?
data. No dead spots, exactly. So these type of graphs allows you to see all these dead spots where you don't see the colors. It's those are the areas where you're not going to get good signal strength. So, but and you're right. This is electromagnetics. This is the CST Studio Suite technology here at DS. This is integrated with SolidWorks. So
Oh,
just
cool.
like our platform products, so you can run analysis, make changes, and then rerun the analysis without having to do the setup. So it follows the same suite of all simulation stuff that we do.
So back to the hot take. Is technology ruining football? You and I were talking about this recently about these antennas because when I first learned about this, I thought that makes so much sense.
Mhm.
What we saw in this World Cup though is maybe they're leveraging it. I don't know. This is this is probably a bigger discussion, but I mean, can it pick up a human hair? And can it pick up if it hits a cable, camera cable? I mean, are those types of things that
Yeah,
they
yeah. Valid
should be, or
question. No, this is valid question, and also very surprising how inconsistent it has been. Like in this tournament, which is why I've been, very emotional about things. But you're right, man. It's like the goal for it is to get into those minute details. Like one of the games happened where the ball in the last second hit a player's hair, and it was caught on these sensors. Like I said, any simple small touch. You're really telling me that a hair is doing that, but when the same ball hits a cable and it's not doing it, so
and
when
maybe it can, but maybe it's also gives an opportunity for that to be the end all say all final answer when do we actually know if that was true or not? I don't know.
yeah, yeah, yes, and that's the hot take, right? Is it ruining football for you? What do you guys think in the chat? Do you think like all this technology that we're going in and in this goal line, would you rather have that, or would you rather have some human interference and like some mistakes here and there, but the human emotion aspect of the game that stays concrete.
I mean,
Uh,
I personally, I think as we talk about the technology of like cleat development, or we haven't really get into that, but they haven't evolved a whole lot. Better materials, they last longer, they're lighter, they're
mhm,
stiffer. I think the Predator cleats of the late '90s when Adidas had for more spin,
mhm,
that's all pretty cool. The ball that makes the most sense. That technology definitely needed to advance past leather.
mhm,
Now we're getting into a situation where we're taking the referee job in their profession maybe out of this a little bit more. Like we have VAR, which is the video assistant referee, and we've seen that be topics of discussion throughout this big tournament. So I don't know, man. Personally, I think that it could be ruining this a little bit, but there's pros and cons to all technology.
yeah,
But that I think that goes to our next topic, and our final take here is the true goat of football isn't a player, it's material science. The true goat of football right now is Erling Haaland. I mean, that's to me is our current goat. I wish he was still playing. But what about you? Are you a Messi fan? I'm gonna make you say it. Put you on the
all
spot.
right, man. No, absolutely not. Cannot do it. Nope. Siu. Let's do a
All right.
Ronaldo over here. Yeah.
All right.
Um,
So
but
so the goat go ahead, finish here.
no, the goat in football. You're right. Players come and go, man. It's like we get connected to players on an emotional level as well. I'm with you, Haaland. Even though in the Premier League he plays for the team that I absolutely despise. Well, there's a lot of teams I despise. It's just I don't know why I'm so emotional about football, man. But you know, he's a great player, and this World Cup he showed what a great player and a human being he is. So I'm Team Haaland as well, just like the rest of the world. So all the best to him. Um, Now, the question, the true goat, if we remove humans out of the goat debate, I think the material, like how the football has evolved from, from actually, I learned a lot from you, Mike. You did your research on how it started in the old Mayans and the Aztecs time, and then the Chinese dynasty, and then how went from like pig bladder to like rubber bladder to polyurethane. That evolution, in my opinion, was perfect.
Yeah, and
Perfect
that's
technology to do that.
credit to the Europeans for the development of the modern day football. As we go through and look at that, because they did dive into the material science aspect of it, even up to it puts us where we are today. But yeah, I think this is an area where you dove into using SolidWorks simulation in our desktop product to figure out exactly like how much different is a modern day ball. This right here is the modern day ball. You
Yep.
can tell by the 4 panel design versus the old leather ball.
Yes. And, Mike, when we were actually recording this thing and I was, playing with the old ball and the new ball, significantly, I mean, there was a difference. You could feel it. But, the one thing I wanted to test live was like, just throw put this leather ball in the water, just let it soak for like, 5-10 minutes and try to juggle the ball. And that was hard. So this is where, of course, when we were working on this project, we did the deep dive into like, how different materials of the balls can perform differently. And we started with like, the modern ball. And we wanted to do a simple drop test. That's all we wanted to do. And then do some nonlinear studies as well, right? So I think we started with the nonlinear dynamic study. And we kind of tricked it into doing like a drop test. I think over here, what the way I was doing this is like, creating, your, of course, you got to have the material selected. You got to have all that data needs to be perfect. So one thing we do say in simulation is garbage in, garbage out. So as long as you have as close to the real world data that you can get, those boundary conditions, the results will be that accurate. So first, I think a lot of research was done into like what goes into the material and all the material properties. We were able to bring that into simulation, create a material, and use that to simulate the structure of this football. Some of the setup stuff that I did, Mike, for this one, where we created an initial condition where this ball is being, impacted at about 4.43 meters per second. I think it was that was just kind of a drop rather than like a kick, because that kick usually happens a lot faster. And then, of course, we utilize some reference geometry aspect to make things a little bit easier for us. We apply the damping, and I think in the final take, I did apply gravity on this as well. And when we ran the analysis, we saw like what the stress plots look like, what the deformation looks like, and oh yeah, that was a very cool animation over there, and it was pretty like we understood like this material and how it was interacting and how it was impacting. It makes sense, and then we switched and we wanted to compare this to the old bottle, old ball,
The
and okay,
leather
over here,
leather key
yeah, the
model,
old.
right? Yep.
Exactly. Over here, you see the response graph as well. For the new model modern ball, and it's in like it ramps up and it kind of like settles down once the ball settles down. So compare this to the old bladder ball, the T model. I think that's what it was called. And we were able to bring in some material properties where what's going to happen when it's wet. We increase the weight a little bit. So of course we made some assumptions in there to run the analysis, do a structural like comparison between the deformation that happens, or even the stress. When a stress sort of travels through the model, and we could see like on a wet new ball, it is fairly even. The stress in it like distributes. That's the word I was looking for. Distributes fairly even, whereas when we were doing this with the wet ball, you could see it was like more consolidated in one space, and it didn't have that ripple effect that was going through the football. So you could tell that there's like a lot of damping that this waterlogged leather ball is providing.
Yes, the original was we looked at a leather dry ball, a leather wet ball, and then a modern day polyurethane with rubber bladder ball. What you saw out of this was the change in dampening between the wet old school leather ball and the modern day ball was dramatic. But and I'm summing up what you said here is the leather ball and the modern day ball actually were pretty similar. It's just that moisture is what where you saw the biggest change.
Yeah. And old
Okay.
game, and back in the day, when you play, and even these days, if it rains or even morning dew, 5 minutes into a game, the ball completely changes. Like, the kicks are different, the way it moves is different. It
That
was fun.
makes sense. I mean, it's a waterlogged ball, and I'm sure it's not fun to kick. A lot heavier, and
Yeah. Heading was harder. And you can see the difference now, Mike, in the modern balls when when it's raining, or when it's like, the dew on the floor. If someone kicks the ball, the modern ball actually skips and it goes faster as soon as, like, for some reason it skips and goes faster. So there's no,
Ah.
damping that's happening with, like, the water. So yeah, it's quite fun to see the progress of, like, how materials came from that and what they do now.
And we were able to kick an old school leather T model and a modern day Triunda and notice the difference in that rebound. We didn't do it with a wet ball just because it was going to be a lot heavier. Didn't want to get hurt. I'm old. But yeah, you could feel that difference between the two.
Yeah.
And we saw it. We were able to replicate the results with simulation and desktop. And what I thought was really cool is through this experiment when we were starting to look at these differences. And I want to kick forward here to kick forward to the side by side. You can see the difference in those plots. Here right away we accelerate up. Notice the steeper curve.
Hmm.
This is what you were just talking about. We have that much steeper ramp up, and then this is where we find that equilibrium, and that dampening there's kind of a natural frequency that occurs here, where much slower ramp up, and then we don't really come to equilibrium at all. And that's because of that dampening with that
Not
moisture.
consistent. Yep.
Yeah. So, simulation, I think it was really cool to see you run through these and get some good data to really digest what's happening between the two. But what I was always curious about was the actual football, like the contact with the cleat. And you came
Yeah.
back with this stuff.
Yeah, man. This was pretty cool because, of course, like, I'm a big simulation nerd. I love doing this stuff. So I want to see what else we can do. So, the SolidWorks simulation products gave us a very good insight, the starting insights, with the material things that we discussed earlier. But then I also wanted to take this next level. So now we have, I'm sure a lot of you know that we've got simulation tools that are on our 3 Experience platform as well, and these are like some high-end advanced tools. So for example, what you were seeing over here, Mike, this is what I call it, or this is what the world calls it, as an explicit dynamic analysis. So these are very so think about any event that's happening and it's releasing a lot of energy. So very short duration, high energy events like a kick or like an explosion. So there's lots that's happening. There's crazy amounts of deformation happening, crazy amounts of movements that's happening, and to be able to analyze all of that, you need a very powerful engine. You need some high powered cloud computing. So we were able to set this analysis up, and I had that study open as well. But I think this video works better. So the way I did this, Mike, I did this in 2 steps. The first step was actually just the ball and keeping the ball pressurized. So on the left hand side under the scenario, you'll see there's a pressurized cavity and the boot kick. So these were 2 separate steps that we created. The first step was to make sure the ball has pressure in it. And then the second step came in when we kicked the ball with that pressure. And that gave us, like, this beautiful boot imprint that you saw in there. And, like, of course, there's the deformation that's going through, the stress values that's going through, and you can see how clearly the ripple effects that going on. And the graph, Mike, the graph that popped up in a second, maybe will show up here shortly as well. That graph was our cavity pressure versus the cavity of that soccer ball becomes a little bit smaller, right? Because it's not being compressed. What happens when things are being compressed? The pressure goes up, right? And you
Right.
could literally see that in that graph, and of course it settles down eventually. So uh, anytime, so this was kind of a take for me as well, Mike, where I started running these studies in simulation and got good results in the desktop simulation. But if I wanted to do like a sort of a full product validation and verification, this is where I would take my studies, and I would actually utilize the high powered advanced physics simulations that I can do on the platform. And again, just like the CST Studio Suite technology, this is also integrated directly into SolidWorks through the task pane. So very easy for us to run an analysis. We don't like the results, do the changes and update our studies, and you can run the analysis again and again. So quite powerful stuff. If the chat and folks watching this haven't ventured out into taking a look at simulation on the platform, I highly recommend it. It's quite powerful.
I think it's a good summary, really, of where those fit. Right, desktop simulation. We were able to do those if-then scenarios and get an idea, like, hey, did this wet leather ball make a huge difference? And we found out, yeah, it did, right? And then we were able to later verify just kicking a regular ball and give them that feel. And we saw that with the initial impact. So there was
Mhm.
a change. We validated that virtually. So if you and I are going to go into designing a new ball, that's where I would start, right? Virtually iterating through all of these different options. We could look at different panel designs now that we know how to model it. What is that? How does that impact changing
Mhm.
thicknesses of materials? All those different small variables you can virtually validate before going to a physical prototype. Where it was interesting that you brought this up was we didn't need to consider the internal pressure on the desktop variation because it was looking more at responsive materials. The
Mhm.
internal pressure would have been probably negated, but at that point, and I always like to say crawl, walk, run, we were kind of crawling to walking through
Yeah.
this. Then we started to ask all these other questions about, well, how much does the pressure actually
Mhm.
change when you're kicking the ball, and how does that impact being modify the results of the kick? And that's when you said, hey, we got to go, this is a lot of analysis. We need the uh, explicit dynamic solver for it. We had availability. The model was done, right? So there was,
Yeah.
we just put this in Simulia physics into the Simulia app, and then we started. You ran through the iterations. We got this, and these are such cool results to see. You can literally see like the laces for in the ball
Yeah.
to get that result. So again, if you're not, if you're new to simulation, it is really that crawl, walk, run mentality, and just doing that early iterations. Or Ron, what did you say? The full product.
Full product verification,
Full
validation,
product
right?
verification is where, like, hey, we need to validate, verify everything before we ship. That's where these higher end packages come in. And again, it's leveraging the same CAD data that we all love to generate.
Yeah.
Hey, Ron, we're getting a little long on time, which is a bummer
Cool.
because my favorite part of this whole project you and I dove into was the flow side. So
Yeah.
how can we let our viewers know to learn more, and where they can review some of this content today?
Yeah, man, I'm with you. That was a lot of fun doing the CFD stuff on flow simulation for this project. Yeah, sorry we're running out of time, but I want everybody, if you guys can, go to solidworks.com/football, and here's a web page that we've created with all the different studies and the videos, and of course Mike looking like a champion over there as well. Please deep dive into it. Let us know what you think. So we broke it. We discussed the structural stuff. We discussed the EMAG stuff, and this the second section we did over here was the physics behind the football curve, and we dove into the Magnus effect and those boundary layers and the turbulences and all that lovely stuff in that particular episode. So please go there, take a look at it, see what you think, and with that, I want to say I hope everyone had a good tournament of the year, and hopefully we're all rooting for the same team now to win the final. I hope we are. But I want everyone to enjoy Sunday game, and just to say, football doesn't stop after this tournament. The Premier League starts. There's many leagues that's going on over the year. So if
True.
someone wants a team to support, please support the Red Devils, the Manchester United team. So go for it.
Hey, and as we're waiting for the next set round of tournaments to come up, check out the SolidWorks tutorial page. This is on YouTube. This has got a ton of great tutorial content that includes simulation, includes design. We've been loading this up. The training team here at SolidWorks is very active with publishing new content. So if you want to learn and up your skills, the SolidWorks tutorial page is awesome.
Yeah,
Really great content to it. And
great
hey,
point.
just to go through our hot takes, spherical balls are the worst kind of balls. We learned that in 2010 when they tried to go to a fully spherical ball. That call is knuckling effect. You need to have some ribbing. Our second hot take: technology is ruining football. It could be, right. I mean, it depends on the perspective. That's a long conversation that we saw some examples of this tournament on where it could be, but also it's super cool, and it's also bringing, advancing the sport as we talk about it. And then third take is the true go to football isn't a player, it's material science. Totally agree.
I'm with that as well. Before we go, there's one quick question that popped up in there. and it was, will there be a 50% discount code for SolidWorks for students soon? Isn't there like a new thing with student design happening these days? Mike, you want to share?
Yeah, there's SolidWorks is now free for all students.
Yeah. So
Yep.
for SolidWorks is free for all students now, guys.
You get
And
SolidWorks standard, so you can man, I don't even know if we have the link to put up on there, but you can probably do a quick search and pull it up. That was a recent release that we just announced at the beginning of the month. So super exciting. I know our CEO Manish was very proud to roll that out. SolidWorks Standard is free for all students, so you can download your copy and start working. So don't even have to worry about 50%. We'll just give it at
yeah,
100.
how about we give you 100?
All right. Well, thank you everyone for joining in. Again, if you have football fans in the family or that you attend school with or you work with, share this design, share the website, solidworks.com/football. Those videos, we did a lot of work. It was a really fun project. Just diving in more of the physics and behind the scenes and the history of the sport we all learn to love. And don't forget to tune in on the World Cup finals. Sorry, the big match finals. That's twice, which is on Sunday, and we can't wait to see who wins Argentina versus Spain. So I'm excited for it.
Far more red in the claret and the blue, and the yellow.
All right, take care, everyone.
All right,
Thanks for tuning
everybody,
in.
take care.